So for our first lecture, I want to talk about a problem that directly relates to the specific problem that I talked about in the introduction. Right? Let's say we have an object and it's falling. All right, the physics guys tell us the distance traveled by that object after t seconds is 4.9 t squared. What I want to know is what's the velocity of the object after t seconds. All right, so we're going to do some calculations, and I want you to see first where the problem is, and second, this is going to kind of start to point us in the direction of the methods we're going to use to eventually solve this. Okay, so I have my object that's falling. I've graphed that distance function, and what I want to do, I want to know what is the speed of this thing when t, make that a 0. That should be t0, the initial time, when t equals 1 second. Okay. So what can we do? Because right now we've got nothing. Right? We've got no tools that'll answer this. But we do have something. The physics and engineering people, they call this the average velocity. Math people, we usually call it, we're a little more general about it, we call it the average rate of change of the function. And you need 2 points. Right? You need 2 points to do this. So I'm going to pick a second point over here. I'm exaggerating this a little bit because I want to have room to draw to insert stuff into the drawing. So I'm going to come over here and call this T1 equals 2. All right, so let's see. What is the average rate of change? The average rate of change is just the slope of the line through the points. So I've got this point right here, and I've got this point right about here, and my average rate of change is the slope of that line. In order to find that, we got a slope formula, right? The average rate of change is s of 2 minus s of 1 divided by 2 minus 1. All right, so now you're going to have to get your calculator out. You put 2 into there for t, and you get 19.6. Whoops, and s of 1, that's minus 4.9 over 2 minus 1. Now you go to your calculator, right? And my calculator tells me that this is 14.7. Okay, well, good. Now, I'm going to want to do this for a few more points because I want to kind of look for a trend here. So I'm going to make a little table. All right, I'm going to make a table, and I'm going to put my t values and my average rates of change. So when t was 1, the average rate of change was 14.7. Okay, so let's try another one. Right? Let's try another one. Bring this in a little closer. All right, so it kind of starts walking this in. Suppose I do t2 equals 1.5. Okay, so you see now my point is here, my second point, and I'm looking for the slope. I'm trying to draw this a little differently so you can distinguish the two. I want the slope of that line. All right, well, if I do that, the average rate of change is s of 1.5 minus, still s of 1, over 1.5 minus 1. You put 1.5 into our function here, this comes out to 11.025. S of 1 is still 4.9, divided by a half, divided by 0.5. Again, you go to your calculator, this is 12.25. So when t is 1.5, the average rate of change is 12.25. Okay, well, that's good. Here's what I want you to do, right? I don't want you to watch me do these calculations over and over again. I want to do a few more of these, right? Let's do 1.1, 1.01, and 1.001. Let's pause this for a minute, right? Get your calculators out. See if you can do those calculations. Fill in the table a little bit, right? Then you can start this back up again and see what my results are. Okay, so when I do this, I get 10.29, then 9.849, and for 1.001, 9.8049. Okay, that's strange. Okay, that's strange. And I want you to think for a minute. I want you to think about why that's strange. Okay, what do the denominators look like? What did your denominators look like as you did this? Right here, let me just maybe add to my table denominators. 2 minus 1 was 1. 2 minus 1.5, 1.5 minus 1 was 0.5. 1.1 minus 1 is 0.1. 0.01, 0.001. The denominators are getting small. They're getting closer and closer to 0. Okay, so what do we expect a fraction to do as the denominator gets closer and closer to 0? Well, just so that I can squeeze this in here. 1 divided by 0.1, that's 10. 1 divided by 0.01 is 100. 0.001 is 1,000. As that denominator gets smaller, gets closer to 0, we kind of expect this to blow up. We expect it to start getting wildly huge, but it's not. It's not. Not only is it looks like it's settling down, right? These two are fairly different. These two are pretty different. There's not much of a difference there, 0.4 give or take. Here the difference is 0.04. If you try one more, let me throw another one up here for you. 0.0001. This is 9.80049. The difference is even less. This was the genius step. This was the point where Newton and Leibniz were looking at this, I'm hypothetically, right? We're looking at this and saying, okay, wait a minute. Something strange is happening here. Something strange. Look at this trend. I'm really thinking that if I keep going, this is going to get closer and closer to 9.8. You know, it's just this weird coincidence. Look up here. 2 times 4.9, that's 9.8. And so the number is even kind of implicitly in there in our formula, right? This idea of what happens to a function as the number gets really close, as the variable gets really close to something, but never actually gets there. And just to be clear, it can't actually get there, right? If we try to use the same point for both points in the formula, the denominator is 1 minus 1, and that's 0. I mean, you can't do that, right? This idea of the function getting closer and closer to something, there's a technical term for this. It's called a limit, right? And we're going to get to that more specifically in the next lecture. A limit, ultimately, is going to be the solution to our problem. Okay. So this is nice. If you're a researcher, this is something amazing to see, right? If nobody has seen this before. But when you do this, when you see something like this, the first thing you ask yourself is, okay, was it a coincidence? Maybe there's something special about this function. Maybe there's something special about this point, about t0 equals 1 that I picked, right? So what you do is you say, well, let me try another one. Right, let me try a second function. So let me clean this up. And we'll try another one. And in honor of Sir Isaac Newton, whose work we're studying here, right? Let's try Newton's law of gravitation. For our example, force equals G m1 m2 over r squared. That's the gravitational force of attraction. That's the magnitude of the force of attraction between two bodies. Now, there's way too much in there, right? Way too much going on in there for us to really play with. So let's make a few assumptions just to make our life easier. First, G is a number. It's a constant, right? It's Newton's constant of gravitation. It's 6.67 times 10 to the negative 11th, right? And again, just to make our life easy, we're just experimenting so far, right? Let's assume M1 and M2 are both 1, right? We're talking about two 1 kilogram masses. All right, so let's see. If I put these numbers in here, this becomes 6.67 times 10 to the negative 11th divided by r squared. And, okay, so let's see. I don't want to, r is, let me make this a function. Let's call this f of r. To make it clear, r is the variable here. Okay. What I want to know is, as two objects are moving together or they're moving apart, right, what is the rate of change of the force at that specific distance? So we got to pick a distance. Let's let r0 be 2. Don't want to pick 1, right, because maybe there's something special about 1. All right, so I'm going to pick another number. Now, here's what I'm going to do. Okay, I want to do my average rate of change again, right? Average rate of change. This is going to be f of r2 minus f of r1 over r2 minus r1. Now, what I'd like to do, because you saw what I did before, right? I started letting the point come closer and closer and closer to my point that I care about here. Let's do this as a formula, right? Let's let r, let's see, I called it, let's be consistent. Let's make that 0. So I'm going to let r2 equal r0 plus some other number, right? That was the 0.1 and the 0.01 and the 0.001 in the last example that I did. So now I can kind of make this into a formula. Right, the average rate of change is f of r0 plus h minus f of r0 over r0 plus h minus r0. All right, so let's put this stuff in, right? I'm going to put r0 plus h into f. This is 6.67 times 10 to the negative 11th over r0 plus h squared minus 6.67 times 10 to the negative 11th over r0 squared. Look at what happens down here. This is nice. r0 minus r0, that's just 0. So that whole thing is just h. Okay, well, that's great. I mean, it's a little messy, but look, this is something you need to get used to. Right? I know in algebra classes, maybe some trigonometry classes, you're used to questions coming out to nice answers. Right? Well, that's not how it works in real world problems. God and nature do not have a preference for integers. Sometimes you're going to get weird things like this, and you need to kind of get yourself accustomed to dealing with them. Okay, so now there's one other thing I can do. R0, I know what that is. It's 2. Right, so I'm going to replace these R0s with 2s. Okay, now I've got a formula. Right, I can put h values in here, and I would put this into Excel. Excel is your best friend when you're doing experimental stuff, numerical stuff like this. And if you do that, look, here's what happens. Let me put some h values up here. Right, we'll do 1, 0.1, 0.01, 0.001. I tell you what, go ahead and pause for a second. All right, go ahead and pause for a second and try that out. Do it in Excel if you like. Right, put these numbers in, put those h values into here, see what you get. Okay, so what are our average rates of change? And when you put 1 in, it's negative 9.1667 times 10 to the negative 12th. When you put 0.1 in, it's negative 1.5340 times 10 to the negative 11th. Okay, there's a pretty decent sized difference there. Next, negative 1.6577 times 10 to the negative 11th. Now it's settled down. You notice the exponent has stopped changing, right? Okay, now I got one more here, right? Negative 1.6458 times 10 to the negative 11. Now, the first two decimal points are the same. And I want one more, right? Obviously, hopefully you can tell I'm cheating. I've got these numbers worked out in advance. If I put 0.001 in here, I get negative 1.6499 times 10 to the negative 11. Now the first three digits have stopped changing. So I'm seeing the same trend. It's not blowing up like we would expect it to do. Okay, like I said, this was the genius moment. Seeing this what would lead you to believe, to continue researching, to say, okay, look, something weird is happening. Let me look into this further. And that's what we're going to do in the next lecture. Right? In the next lecture, we're going to talk about that concept of a limit, or we're going to look at it kind of just in a plain English version, just kind of continue our experimenting, right? See what it does, kind of refine a little bit, make sure it has the behaviors that we want, that we expect, right? Then in the lecture after that, we'll talk about the formal mathematical definition of the limit, and that'll really kind of be the high point, well, be a high point of this chapter.